today I will discuss about the grating diffraction experiment, and also I will demonstrate the grating diffraction experiment. So, let us see the working formula for this experiment. So, basically aim of this experiment is to determine the wavelength of the prominent lines of mercury. Okay. It can be any other source. So, in our lab we will use mercury source. So, it has basically many spectral lines, but there are few are prominent, intensity high. So, we will determine the wavelength of those mercury lines, and then we will find the resolving power of the grating, as well as we will find the dispersive power of the grating. So, this is the diffraction grating experiment. From this experiment, basically we can measure the wavelength of a source. It can be mercury, it can be hydrogen, it can be cadmium. Okay. So, then we can find out the resolving power as well as dispersive power of the grating. So, you know this grating is is basically N-slit device, single slit, double slit, and this is N-slit device. So, that is grating. So, the grating element D is basically so slit, it has opaque part. If you consider a slit, it has a open part. Okay, say that is A, and for double slit there is two open part, and this in between there is a opaque part. So, distance between the middle of this two slit, that is basically distance of the middle point of the two slits. That means half from here, half from here. So, this is the A by 2. So, that is A slit width plus this separation of these two slit. If it is B, so A plus B, so that is the D. Okay. So, that is called grating element. Okay. So, now this grating experiment, diffraction of grating basically is the Fraunhofer type of diffraction. You know this, there are two types of diffraction. One is Fresnel's diffraction and another is Fraunhofer diffraction. So, Fresnel's diffraction, one of the source or the not one of the source or screen, one of them will be at finite distance. If both are at infinite distance, then that is Fraunhofer type. If one of them or both are at finite distance, then the diffraction we will see, that is the Fresnel type diffraction. Okay. So, in this experiment is the Fraunhofer type experiment. That means object will be at infinity and image also will form at infinity. But in laboratory, in finite distance we will do the experiment. So, for that basically, so infinite distance means object is at infinite distance means, so light will fall on the grating. So, those lights are parallel light. Image will form at infinity means the diffracted light, they will meet at infinity. So, that means the diffracted ray is also parallel. So, they will form image at infinity. Okay. So, to do this in finite distance, so we have to make the setup equivalent to that infinite distance. So, how we can do? Basically, we use convex lens. So, if we use convex lens and source as a finite distance at focal point of this convex lens, so other side of the lens the light will get parallel rays. So, it is a equivalent to that object is at infinite distance. Similarly, the diffracted rays, parallel rays are coming. Okay. So, to put them at a screen, so we have to put the focal screen at the focal point of that lens. So, here also we have to use convex lens to form the image at finite distance. So, that is why that means if we use collimators, okay, if we use prism spectrometer, their collimator is there. So, this collimator basically it will produce parallel rays. So, that will fall on the grating, and then diffracted rays is set, different sets of parallel rays will get. So, each set will give the image, okay, for a particular order. Okay. So, it depends on the diffracted angle. So, we will use telescope. Telescope have convex lens. So, and it has eyepiece. Okay. So, we will see the image through eyepiece. The image will form at the focal point of the telescope lens, and that at that focal point is basically this crosswire are put there. So, on crosswire this image will form, and through eyepiece we will see that one. Okay. So, this is first condition to see this diffraction, Fraunhofer type diffraction. Second condition is that light will fall, parallel light will fall on the grating perpendicularly, okay, normal incidence of light. Okay. So, that means incidence angle is 0. Okay. So, we have to make sure, we have to set the grating in such a way that from collimator whatever lights are coming, so they will fall on the grating perpendicularly. Okay. So, we have to set grating at that should be perpendicular to the normal light, to the light, parallel light from the collimator. Okay. So, because the working formula we will use, that formula is only valid for perpendicular incidence or normal incidence, right. So, this second condition has to be fulfilled. And in our case, there are two types of grating, reflection grating and transmission grating. Okay. So, here we will use transmission grating. So, we will see the diffracted ray in other side. Okay. If it is reflecting grating, so one will see the image in the same side. Okay. So, here we will use transmission grating. Okay. So, if this light is monochromatic light, okay, so other side we will see the fringe, we will see the fringe of different order. Okay. So, this type of fringe you will see, okay, they are of different order. So, from central order to in both sides we will get this order, first order, second order, third order. So, other side also we will see the symmetrically we will see. So, difference. So, this can be one. Another is if we use not monochromatic light, it has light of different wavelength like mercury. So, different color of light, okay. So they will fall on this grating, and other side for each color we'll get the fringe pattern, okay. So that is first order, second order, third order. Similarly, so other side also first order, second order, third order. And if you look at the only first order fringe, so there you will see the lines of different colors. So say this is of different colors, so this is the first order, okay. Again it will come symmetrically from left side and right side. So you will get the second order again at higher distance, okay, higher angle. So you will see the second order, third order, etc., etc., okay. So that will be that are basically we tell the principal maxima. So condition for principal maxima is d sin theta equal to n lambda. So d is the grating element, sin theta. So this theta is basically this refracted angle, okay. N is the order of the fringe, okay, and lambda is the wavelength, okay. So then we want to find out the lambda wavelength. Wavelength is equal to d sin theta by n, okay. So d sin theta by n, so we have to know the grating element. So generally this is supplied, actually it's supplied is the number of lines per unit length, per unit width basically. So generally company supplied this per inch, number of lines per inch. So we prefer in centimeters. So whatever number of lines per inch, so number of lines divided by 2.54. So that will be the number of lines per centimeter, okay. So so if you know the number of lines per centimeter, so then 1 by that number of lines per centimeter, so that will be basically d. That will be basically d. So d is basically we can calculate from the supplied data, and only we have to measure basically this theta for different lambda. We will get in first order n equal to 1. So in first order, so what are the theta for different color, okay. So if you can measure this angle of diffraction theta for different lambda, so we can calculate lambda, okay. So so using this formula, measuring the diffraction angle for different order, for different color, we can calculate the wavelength. Now this grating, like it's a prism, like prism, this grating have again resolving power and dispersive power, okay. Resolving power means this to close wavelength, whether grating can resolve or not, means whether this to close wavelength we can see in spectra. So that's the basically resolving power. So that's the lambda by del lambda. So that is equal to n, small n. This is basically small n, that is basically order, as I told, first order, second order, third order, okay, order of diffraction. And here capital N, that is basically number of lines. Number of lines on the grating, it's not per centimeter, it's basically the number of lines exposed by the light. So here you have grating, it's the say its width is 1 inch, but your light is not falling on this 1 inch means 2.5 per centimeter, it is falling on the 1 centimeter. Okay. So this in 1 centimeter, how many lines are there? So that is basically capital N. Okay. So this I have written equal to NMX. N is order small n. M is basically MX. M is basically number of lines per inch into X is the width of the source. Width of the source. Okay. Or the width of the width of the source slit, we can tell that width of the source slit, so that this width of the source slit, so that the exposed width of that grating we can tell, so that is X. So number of lines will be M into X. Okay. So here you will get from this what is the resolving power of this grating. So all data are available with us. So here generally what we do, we here our exposure, that exposure of the light on this slit is around 1 centimeter. So that's why, so X we take 1. So that basically N into M. So here for different order basically we can calculate the resolving power. So resolving power mainly will depend on the M, number of lines per centimeter, So it will depend on that factor. And dispersive power is d theta by d lambda. If you find out from here d theta by d lambda, so this is n by d cos theta. Okay, n, small n is order, and d there's so that 1 by m basically this d, and theta will measure this theta. Okay, for different order we will measure this theta. Okay, so we can calculate the dispersive power of the grating. Okay, so these three are the working formula. Lambda equal to d sin theta by m, or sin theta by mn, small m n. Okay, m will be calculated from the given data. Only we have to measure theta. So we can for different wavelength and for different orders, and then we can, from that same data we can calculate the resolving power. From same data we can calculate the dispersive power of the grating. Okay. So what are the measurement we have to do is are the following. So experimental data, prism spectrometer we will use. So you are quite familiar. Okay, with the prism spectrometer, because lot of experiment already we have done using the prism, but this is the first time I am demonstrating using the prism table where we will use the grating instead of prism. Okay. So Vernier constants of the spectrometers, Vernier 1, Vernier 2, so we have to note down. Okay. So then number of lines per ruling, number of lines or rulings per unit length. Okay. So that m, small m is basically, so it's the per centimeter we have to say, if it is given per inch, so we have to convert it per centimeter. Okay. So in our case we will see what is the value. Then you have to find out the grating element, d equal to 1 by m in centimeter. Then table 1, set the grating surface for normal incidence of light. As I told, this actually first spectrometer you have to level and then set for the parallel rays, use Schuster's method. So everything, the spectrometer is ready for the experiment using the grating. So here the table I am showing. So after that, what you have to do with the grating? So we have to set the grating surface normal to the incident light. Okay. So how to do that? So we have to take direct reading of the telescope without grating. Then telescope is rotated through 90 degree and set at some angle. Okay. So we'll note down that angle. So here this is the direct reading, and here this is the at 90 degree. What is the reading? Okay. So this difference should be the 90, and then reading of the prism table for 45 degree incidence. Okay. So we'll put the grating on the prism table, and prism table will rotate in such a way that in telescope at 90 degree we should get the reflected light from the prism surface. Okay. So when we will get the prism reflected light from the prism surface, so then this prism that grating is basically the grating surface is at 45 degree with the light, incident light. Now from that position, prism table is rotated by 45 degree more, or so it depends on, or 135 degrees. So if you rotate in opposite direction, so it should be 135, and set at angle means that reading will take. Okay. So this is the first table we have to do, and then we will go for the second table. So the second table is basically data for this angle of diffraction for the lines of different colors and orders. Okay. So we will note down the angle for different diffracted lines of different order and colors. Okay. So order number we are writing here. Actually we will take only first order and second order. Higher order, this intensity generally is decreased, so it's difficult to take. Okay. So first order, second order for one color, say its color is blue. Okay. So for blue color, for first order we will take reading from vernier 1 and vernier 2. Okay. So for second order we will take vernier 1, reading for vernier 1 and vernier 2. So main for vernier 1, vernier 2, main scale reading. So reading for the diffracted image with the telescope at the left. So we'll start from one side. Okay. So we'll set at second order. Okay. And then as I told, symmetrically we'll see this. From central fringe, central order. So left side and right side we will see first order, second order, third order, etc. This other side also we will see first order, second order, third order. So that's why we have written left order, and this is the right order, right side order. Okay. So we'll take for first order and second order for a particular color. So this color is basically extremely left for second order. So we'll start from there. So second order of that color, then first order of that color, or what we will do, from extreme left we will move. So, we will get this second order. So, for second order, first we will take reading from vernier 1 and vernier 2 for blue color, then green color, then yellow color, then other colors. Okay. Then we will move still in same direction. Then we will get the first order. So, first order for blue color, green color, yellow color we will note down. Okay. Then in same direction we will move, and we will go to the other side, right side of the central fringe. Okay. There we will get first order first. Okay. And then there we will get this color basically. So, we will note down for the first order for different color and continue to move in the same direction, and we will get the second order. Okay. So, for second order for different color you note down the angle. Okay. So, note down the reading. Okay. So, now difference of these two reading will give basically 2 theta. Okay. So, then we will find out the mean 2 theta from order 1 and order 2. Okay. And half of that will be basically angle of diffraction. Okay. So, for different color and for different order we will get angle of diffraction theta. Okay. So, basically for first order and second order this angle of diffraction are same, right. So, we will note down the average value of this angle of diffraction for different colors. Okay. So, after that calculation, determination of wavelength of lines from colors of different colors of mercury source, right. So, here this it's m equal to 1 by d. So, this is the same value, okay, supplied value basically or calculated value. Then for different color, for different orders, okay, okay, angle of diffraction will note down. So, from there we can calculate this lambda. Okay. So, then we will take the mean lambda. So, this is one way. Another way also, plotting graph one can find out. If you plot order versus, I think, what is that formula? This is the formula. Okay. So, if you plot order versus sin theta versus order. So, in that case basically you have to at least you have to take 3-4 order, but it is difficult to get if getting is not very good. Okay. Quality is not very good. Beyond second order it is difficult to get. So, plotting graph also one can find out. So, sin theta versus n, and then from the slope one can find out that slope will be lambda into d. So, d is known. So, lambda can be find out. So, we are not going to use that method because in our setup only we get up to second order. Other higher order is very, very weak. So, we will calculate basically mean wavelength from 2 order. Okay. So, then you can calculate the dispersive powers or resolving powers. Okay. So, for that for different color, different order, so angle we know already. So, number of getting lines illuminated by the collimator. So, this capital N equal to small m into x. So, here basically we will take the m value, as I told that we will not measure this x, approximately our exposure is 1 centimeter, and resolving power we can calculate. So, here also this capital N will take equal to m, okay, lines per centimeter, and then using this formula angular dispersion we can find out. Okay. So, this is the experimental data we can analyze and get different parameter, and then you can calculate the error. So, for wavelength lambda equal to d sin theta by n. So, that is sin theta by nm. Okay. So, take log and find out this delta lambda by lambda equal to actually this term will contribute, other term this is the number, basically number of order counting, so no error, and this is ln m. So, this we are calculating from supplied data, so no error from here. So, only this part will contribute to the error. So, this will be basically delta theta by tan theta. Okay. Here I have written 2 delta theta because theta equal to theta 1 minus theta 2. It is difference of 2 reading. Okay. So, that is why we have written 2 delta theta, whereas delta theta is the least count or Vernier constant. Similarly, for resolving power R equal to m n x. So, here if we measure this x with using the slit, micrometer slit, so then there will be error, but in our case we will not measure. Okay. We will only consider x is 1. Okay. So, then for this case there is no probable error. Okay. Similarly, for dispersive power, this is the formula, take log and differentiate, you will get this. So, again this delta n by n, it is a 0, delta m by m also we are calculating, it is a 0. So, only this part will contribute. So, basically this del theta by cot theta or tan theta into del theta. So, that will be the error. So, this theta we are measuring basically. So, there will be error. One can calculate the error in dispersive power. Okay. So, this is the basically before doing experiment, this all these things we have to understand, and we have to keep ready this your table. So, I will stop here. Thank you for your attention.